Ah, yes. That's the sound of Mother Nature not caring at all about cooking you worse than your last charred campfire marshmallow. But you're not completely helpless. You've got math. We're gonna go down the iceberg of lightning math, starting with keeping you safe and then figuring out just how close Mother Nature came to reminding you why ultralight hiking umbrellas can be a bad idea. Let's set the scene. You're an ultralight alpha whose overpriced gear has never left your gear closet. But by God, today's the day. And you venture out onto the trail, only to find lightning threatening your precious gear. While the idea of it burning off a few more grams does have a certain appeal, you've still got enough of a survival instinct to know that it's time to take action. And that gets us to the top of our iceberg. We're gonna put safety first with our first bit of math, which, luckily for us, is just counting. We'll find that math in the 30-30 rule, which, according to the National Weather Service, quote, offers the best lightning safety guidance for the general public. I'll let them explain it.
When you see lightning, count the time until you hear thunder. If that is 30 seconds or less, the thunderstorm is close enough to be dangerous. Seek shelter. If you can't see the lightning, just hearing the thunder is a good backup rule. Wait 30 minutes or more after the last lightning flash before leaving shelter.
So if your time, T, is less than or equal to 30 seconds, then your wait, W, needs to be greater than or equal to 30 minutes. Okay, so now you're safe. But if you're still thinking, gee, I also really need to know just how far away that lightning strike was. Well, I hope your pack liner is sealed tight, because we're going deeper. The next layer down in our lightning math iceberg, dibs on that band name, is a quick rule of thumb requiring only basic arithmetic. To get an approximate distance in miles, take the time you counted in seconds and divide it by 5. Or for kilometers, divide it by 3. That's it. Turns out this is just an application of one of the physics formulas you might actually still remember from high school. Distance equals velocity times time. Sound travels at about 1/5 of a mile per second, or 1/3 of a kilometer per second, so that's your velocity. Simplify that to division, and you've got this rule of thumb. Or just think of it as divide by 5 for my, divide by 3 for me, ters, kilometers. Okay, whatever. You can come up with your own mnemonic. Let's move from 3rd grade integer division to 4th grade decimals. I mean, you probably have a calculator in your pocket on your hike, so why cheap out with integers when we can go full decimal? Let's start with distance equals velocity times time. For velocity, we'll take the speed of sound at 68 degrees Fahrenheit, which is 767 miles per hour, or 767 miles per 60 minutes, or 767 miles per 3,600 seconds, which is equivalent to 0.2131 miles per second. If we switch multiplying by this number to dividing by its inverse, we end up dividing by 4.6936, which is pretty close to the 5 in the rule of thumb. This works the same way in metric, where we'll end up dividing by 2.9164. Again, pretty close to the 3 in the metric version of the rule of thumb. Okay, if you've made it this far into the video, I know you're here for some unnecessarily complicated camp math. And I'm gonna deliver like 2 is 1 and 1 is none. You might think that things like air pressure, humidity, and temperature will affect the speed of sound. There's gotta be some incredibly complex physics formula that takes all this into account, right? Well, yes and no. Temperature will matter, but nothing else will. So, spoiler, we're going to be able to boil this all down to a formula that looks like this. You take the temperature T, add something to it, take the root of that sum, and multiply by something. That will get you the speed of sound in air, C. Those somethings are just numbers that change depending on which units you want for temperature and distance. We'll calculate this out for Fahrenheit and miles per second, and for Celsius and kilometers per second. To get there, let's start with this mess. That's the formula to calculate the speed of sound in an ideal gas. We don't need to get into what an ideal gas is, but air is close enough to one that we can use this formula. In the formula, C is the speed of sound in an ideal gas in meters per second. Gamma is the adiabatic index of the gas, a constant specific to each gas. R is the molar gas constant, or about 8.3145. T is the temperature in degrees Kelvin, and M is the molar mass of the gas, another constant specific to each gas. So if we calculate this for air, we'll need the constants for air. Gamma is 1.4 and M for dry air is 0.02896. Before we start plugging in constants, let's first separate them out. Now we can plug in all the values, which works out to a coefficient of just over 20. That gets us our first formula in this form, with the temperature, T, in kelvins, the multiplier, M, equal to about 20, and the addend, A, equal to 0. This will get you the speed of sound in air, C, in meters per second. That means the only important input is temperature. Let's turn to Dr. Hanna Pamela of the AGH University of Krakow for what's going on here.
The speed of sound in air depends only on constants and the temperature, and not on the air pressure or density, as is sometimes claimed. Humidity also has an effect on the speed of sound, but the influence is so small that it can be neglected. The temperature is the only important factor.
So no need to worry about the lower air pressure at altitude or humidity. The temperature is the only thing that's going to meaningfully change how quickly the sound of that thunder gets to your ear.
Ooh, that was thunder.
We've got a formula, but it needs the temperature in kelvins. Now I know us science geeks think that kelvins can be pretty cool. Absolutely cool, in fact. But those who are not absolute zeros might still want to work with units that are a bit less cosmic and a bit more atmospheric. We'll also want to switch the unit for speed from meters per second to something more practical. Miles per second or kilometers per second. First, to go from Celsius to kelvins, just add 273.15 to the temp in Celsius. Now we just swap that in for the temp in kelvins. And to get from meters per second to kilometers per second, we just divide by 1,000. That's it. And that simplicity makes me want to shed tears of Celsius joy when I know what's coming next, which is imperial units and the mess of Fahrenheit. This is the formula to convert Fahrenheit to Kelvin. Let's first simplify this a bunch until there's no coefficient on the temperature. Now we can swap that into our formula and simplify a bit. And finally, we can multiply by this ghastly number to get from meters to miles. And huzzah! We've now got our formulas to get from the air temperature to the speed of sound in air, from kelvins to meters per second, from Celsius to kilometers per second, and from Fahrenheit to miles per second. To get the distance, just multiply each of those by the time, T, in seconds. Using the speed of sound as adjusted for temperature gets us pretty darn close. But if we truly want to simulate the real world in our little matrix, we're not quite there yet, although we are at the bottom of our iceberg. There's a number of things that we haven't included in our calculations. Humidity affects the molar mass of air a bit. Air not quite being an ideal gas may have a slight effect on the calculations. And we haven't even gotten into wind's effect on the apparent speed, direction, and distance relative to an observer. But you know what? Since getting a good vector measurement of the wind between you and the lightning seems pretty unlikely, and the other things only have a negligible effect, I'm going to leave this deepest part of our iceberg as homework for you. Post your work in a comment below if you ever complete the assignment. So now that you've got the deets on all but the murkiest parts of our iceberg, how much have we actually improved the calculations for the average camper in the great outdoors? Short answer, not much. Check out this table, which covers pretty much all the temps that a human is likely to be out in. And the speed of sound is always pretty close to dividing by 5 in miles per second and dividing by 3 in kilometers per second. And that remains true in the bolded temperature ranges where lightning is most common. So, after all that highbrow math, guess what? We're right back to the simple divide by 5 for my, divide by 3 for me. And no complaining in the comments about this mnemonic unless you've got a better one. And now, you're also ready for all the lightning math your heart desires. Just think of it as something to wow your hiking buddies during your next 30-minute wait from the 30-30 rule. I'm sure there's absolutely nothing they would rather hear you geek out about while avoiding Mother Nature's wrath. Subscribe for more camping tips and tricks, and yes, more camp math too.
I just noticed it's actually hail. It was rain before. That would explain why I'm not getting too wet. This is gonna get slippery. There are a lot of people still caught in the rain down there. Oh gosh, that's getting closer.